Section 5.5 Applications. In this section we're going to take a look at how we can use logs to solve word problems. Okay, we're going to look at quite a few different types of word problems, so let's get started. The first set of word problems have to do with compound interest. So here we're going to use this formula. There's two formulas here for compound interest, depending upon how the interest is calculated. So the first formula is this. You have A is equal to P 1 plus R over N NT. Okay, so what are all these quantities over here? Okay, the first thing is this is the amount. Well, let's start with this side. P is the principal, how much money you invest. Okay, P is the principal. That is amount of money invested. Okay, R is the interest rate. So this is the interest rate. Let me write this down on the bottom, it might be easier. I'm trying to crowd this. So P is the principal. It's the dollars invested. Okay. R is the annual interest rate. When you invest money in a bank or something, they pay you interest at a certain rate. That's what R is. T is the time in years. And N is the key factor over here. N is the most important thing in here. It's the compounding time. Time per year. So how often do you get interest? Okay, if you get interest annually, then N would be 1. If you get interest semi-annually, then N would be 2. If you get interest monthly, then N would be 12. If you get interest daily, then N would be 365, and so on. Okay, so N basically represents that. So what is A then? A is the money, the amount of money, okay, in the account, amount of money at the end of T years. That's how much money you will have at the end of T years. Okay, so that is the first formula for for compound interest. The second formula that we're going to use for compound interest is this one. A is equal to P e to the RT. P, R, and T and A are exactly the same as before. The only thing that changes is we don't have N, because now the money is compounded continuously. Okay, the money in this formula is compounded continuously. So basically you're getting interest every second. Okay, so this is the formula we're going to use if the money is compounded continuously. If the money is compounded for a certain number of times a year, then we're going to use that formula. Okay, so these are the two examples of compound interest. So let's take a look at a couple problems. Okay, just to see if you understand how to do these problems. Okay, so let's start with something simple, just calculating compound interest. Okay, so we can say find the balance in an account that had an initial investment of $1,000, okay, compounded of $1,000 at an annual interest rate of 6%, okay, for 2 years. Find the balance in an account that had an initial investment of $1,000 at an annual interest rate of 6% for 2 years. Now, the money is compounded quarterly, two ways: quarterly and monthly. So you want to find how much money is in the account if the money is compounded quarterly or monthly. Okay, so let's take a look at how to do this problem. Okay, alright, if it's compounded quarterly, n is going to be 4, and monthly it's going to be 12. So all we're doing is using this formula to just figure out how much money you have in the account at the end. So let's do the first part. Your principal is $1,000. The rate is 6%, so it's 0.06, and the time is 2 years, and n is equal to 4. So we want to find how much balance is in that account. So A is equal to P1 plus R over N, NT. So we get 1,000 times 1 plus 0.06 over 2 times 2 times 4. I'm sorry, this should be a 4. So it's just a matter of doing calculator work. We just need to punch it into the calculator to figure out how much interest we have here. Okay, so we can just enter it in just the way it is. We have 1,000 parentheses 1 plus 0.06 divided by 4 close parentheses. Raise that to 2 times 4 is just 8. So we get $1,126.49. $1,126.49. That's how much money you'll have at the end of that period. If I do the same problem again, except this time n is 12, okay, so we get A is equal to 1,000 times 1 plus 0.06 over 12 times 2 times 12. So let's do that again. I'm just going to use that formula again. Just go in and make some 2 times 12 is 24, and instead of dividing by 4, we're going to divide by 12. We have $1,127.16. So we have $1,127.16. Okay, so that's how we use that formula. Let's do the same problem again one more time. If it was compounded continuously, so in that case A would be P e to the RT. You're getting interest every second basically. So we get 1,000 times E, R is 0.06 multiplied by 2. So let's see what we get. So we get 1,000 times second and division key to get E raised to. So we get parentheses 0.06 times 2. Okay, I keep forgetting multiplication, times 2. And we end up with $1,127.50. $1,127.50. Okay, so that's how you use these formulas, but that's not really what we want to do. We are more interested in logs. How would logs get involved in this problem? Well, they will come into play when we want to find the unknown exponent. Remember, we talked about it. Anytime you want to find an unknown exponent, you have to introduce logs, right? So that's how logs are going to come into play. So let's take a look at an example. So like, find the time it takes $5,000 to double if invested at a rate of 6%, 8%, let's do 8%, okay, compounded. We'll do it two ways, semi-annually and B, continuously. So the question is, how long would it take if you invest $5,000 to double, so to become $10,000, if invested at a rate of 8%, compounded semi-annually and continuously? So let's do the first problem. So the P is equal to 5,000. We want to end up with 10,000, the amount we want to end up with at the end of some time. We don't know the time because I want you to find how long. The rate is 8%. So it's equal to 0.08, and n in the first case is 2 semi-annually. So we're going to use this formula. A is equal to P 1 plus R over N and T. So let's plug in things we know. We have 10,000. And if you don't want to write it as 10,000, it would be better to write it as 2p, because you want the amount you end up with to be twice what you started with. Principal is what you start with. So even if had they not given us p, we could have done this problem. We would have just had to figure out what the amount we ended up with. If it was triple the amount, we would have used 3 and so on. Had they said that you start with $5,000 and you want to end up with 8,000, then we would need to know what A is. Okay, so just keep that in mind. We could have easily replaced this with 2p to do that. So we have 5,000. We have 1 plus r, which is 0.08 over 2 raised to 2t. Now my unknown over here is t. So I know I have to introduce logs, but keep in mind there's one very important thing to remember when you introduce logs. Whatever the exponential number is, this is the exponential number. You have to isolate that before you can introduce logs always. If you go back and look through the last section when we did logarithmic equation, we always isolate the exponential numbers were already isolated when we introduced logs. Okay, so the first thing we have to do is get rid of this. This is attached by multiplication, so I'm going to start by dividing both sides by 5,000, so we get 2. When I divide this side by 5,000, it'll cancel. So we get 1 plus 0.0 excuse me 0.04 raised to 2t. Now that we isolated the exponential number, this is the base, this is the exponent, so that's my exponential number. Now that we isolated that, now I can introduce logs. I get ln of 2, okay, is equal to ln of 1.04 raised to 2t. Now how do I finish solving it? One of the nice properties of logs was what? If you're taking log of an exponential number, the exponent can come in the front. So we get ln of 2 is equal to 2t times ln of 1.04. I can divide both. So you want to solve for t, so I can divide both sides by 2 times ln of 1.04. So I get t is equal to ln of 2 over 2 times ln of 1.04. And that'll give us the time. So let's do this. And make sure you write your answer in terms of a sentence, because it was a word problem. They asked you the question in terms of a sentence, so make sure you do that. We get ln of 2, close parentheses, divided by, I'll open parentheses, 2 times ln of 1.04, close parentheses. So we get 8.84. So we get 8.84 years. So it'll take roughly 9 years for the amount to double at 8%. Okay, if it's compounded semi-annually. Okay, let's do the same problem if it's compounded continuously. My numbers are all the same. P and everything is the same, so we just use a new formula. So I get A is equal to P e to the RT. So we get 10,000 is equal to 5,000 e to the 0.08 t. Okay, so that's what we have. Again, I want to solve for t. T is an unknown exponent, so I need to introduce logs. But to do that, first I have to isolate the exponential number, this number first. That is my exponent, that's my base. I want to isolate that. So divide both sides by 5,000 since it's attached by multiplication. So I get 2 is equal to e to the 0.8t. Now I can introduce logs. So I get ln of 2 is ln of e 0.08t. Once again, the nice thing about log of an exponential number is I can bring that exponent in the front. So I get ln of 2 is equal to 0.08t times ln of e. Over here the number and the base are the same, so there was a log property that told us that the ln of that is 1. We're using this property. When you take log of a number b and the base is b, if the number and the base are the same, the log of that is always 1. We have ln of e, the base, this is the same thing as log of e base e, the base and the number are the same, so we get 1. So now we divide both sides by this quantity to get t by itself, so we get ln of 2 divided by 0.08. So we can divide that on our calculator, so we can take ln of 2 divided by 0.08. So we get 8.66. So it takes 8.66 years to money to double if it's compounded continuously. Okay, so that's how you do these problems. They're fairly straightforward. Okay, just let's say in the last example they said that instead of doubling they wanted the amount to be, let's say, $8,000 instead of doubling. Well, let's increase it. Let's say they wanted $12,000. So how would you do that? Okay, compound it continuously. You do the same thing. We have a is equal to p e to the rt. So you replace a with 12,000 is equal to 5,000 e to the 0.08t. Once again, I want to solve for t, unknown exponent, so I'm going to introduce log. So let's isolate this first. So divide both sides by 5,000, so you get 12 over 5 is equal to e to the 0.08t. We're going to introduce logs on both sides, so you get log of ln of 12 over 5 is equal to ln of e to the 0.08t. Bring the exponent in the front. So we get 0.08t times ln of e. ln of e is 1 because the base and the number are the same, so t is ln of 12 over 5 over 0.08. And that gives you a value for that. So we get ln of 12 divided by 5 divided by 0.08. So we get 10.94 years. Okay. Now, I do want to let you know they could have easily said, like in this problem I mentioned that before, they could have said find the time it takes for the principal to triple, let's say, if this is invested. So they didn't tell us, everything else is the same. They didn't tell us the initial amount what you started with, but we know this. We want the amount to be how much at the end? Triple, 3 times what you started with. So in this case, everything stays the same. If you look at it, a would be 3p and p would be just p. And then I want to isolate this exponential number, so p's can cancel. You can divide both sides by p, so this becomes 3. This becomes 3. This becomes 3, 3, and then you can find the value. So then you can go ln of 3 divided by 2 times ln of 1.04, and we get 14 years roughly. Okay, so this is going to be roughly 14 years. Okay, so keep that in mind. They don't have to give you the amount, but if they told you some relationship with how much you want to end up with, 3 times the principal or 2 times the principal or whatever. Okay, so those are compound interest problems. The next problem that we're going to take a look at has to do with growth and decay. Okay, so let's start with the first formula. The growth formula is given by this. You have Q of t is equal to Q naught e to the kt, where Q of t is equal to the population at time t. Population at time t. Okay, how many people are there, or how many bacteria are there, or how many rats are there, or whatever your population you're looking at. Q naught is always the initial population, how many you started with. Just like in terms of money, it would be your principal. Principal is how much you start with. K is your growth rate. How fast is the population growing? It's your growth rate, like your interest rate. And T obviously is just the time. Okay, so this is a formula for growth. Pretty okay with that? Now, you can also have a similar formula for decay, and especially that happens. So this is basically population growth that we are talking about. There's another formula that has to do with decay, which looks exactly the same. The only difference is now you have a KT. So this formula is for radioactive decay. Radioactive decay. And it makes sense when the exponent is positive, that means a function's increasing, so population is growing. When the exponent is negative, then you remember it's like this, so then the function's decreasing. So what is radioactive decay? If you recall, radioactive material always emits radiation. As it emits radiation, it loses its mass, so it decays in mass. So in this case, Q of t is the amount of radioactive material present at time t. Okay, and Q naught is the initial amount, how much you started with, and K is the decay rate, how fast it's decaying. Okay, so as a radioactive material emits radiation, it loses its mass and it'll get smaller and smaller. But keep in mind, it'll never get zero, because when you think about it, if this is T and this is Q, because instead of F and X we have T and Q. Q is the amount of material. As you can see, it gets smaller and smaller. Will this graph ever go to zero? No, it gets closer and closer to zero, but never goes to zero. So the amount of radioactive material will never disappear. It'll just get smaller and smaller and smaller and smaller. Okay, it's just that usually the radioactive material is harmful initially because it has got high concentration. As time goes by, it decays, and then it reaches a point where the amount of radiation that it's emitting is so little that it's no longer harmful to the humans. Okay, now one very important thing needs to be calculated whenever we talk about radioactive material, and that is half-life. So what is half-life? Half-life will be denoted by T sub h, which is the time it takes the initial amount of radioactive material to decay to half the amount. So half-life is how long it takes for the radioactive material to half the radioactive material to decay. So let's calculate half-life, because once we calculate it once, we don't have to keep doing it every single time for every problem. Okay, so what does it mean for half-life? So Q is the amount of material you have left, right? So Q after half the time, after some time t, would be half of what you started with. So it'll be Q naught over 2. Q naught is what you started with, so you'll end up with Q naught over 2. Okay, so let's solve this. So formula is Q is equal to Q naught e to the negative KT. Q is now Q naught over 2 because you only have half the material left, is equal to Q naught e to the negative K times T sub H, because that's my half-life. Okay, so after, let me write this better, Q of T sub H, after some time T, the amount of radioactive material you have left is half what you started with. That time is called the half-life, so I'm denoting that by T sub H. So now I want to solve for T sub H, my unknown exponent. So I need to introduce logs, so I need to isolate this exponential number first. So I want to get rid of Q naught. So I divide both sides by Q naught so they will cancel. So I get 1/2 is equal to e to the negative K times T sub H. So we can introduce logs on both sides now. So we get ln of 1/2 is equal to ln of e to the minus K times T sub H. I'm going to use the log properties here. One of the log properties is what? If you have a quotient, you can take the log of the first minus the log of the denominator, log of the numerator minus log of the denominator. And out here, because I'm taking log of an exponential number, I can bring that exponent in the front, and I get ln of e. We know ln of e is 1 since the base and the number are the same. And over here we know that ln of 1 is 0 because log of 1 is always 0. So we get minus ln of 2 is equal to negative K times T sub H. So I want to divide both sides by negative K, so the negative signs will cancel. So you get T sub H is equal to ln of 2 over K. So this is the formula of a half-life. Now that we know that, we don't have to do that for every single problem. The most important thing is, once we know T sub H, we also know K. I can cross multiply these, so I get K is equal to ln of 2 over the half-life. So that's a better formula to know. Okay? Alright. So these are the formulas we need to do problems on growth and decay. With both of these problems, they will give us most of the information. They won't give us K. So your first goal will be to find K. Once we have K, then we can find whatever else they want us to find. So keep that in mind. We always want to find the growth rate or the decay rate, okay? Unless they give that to you. If they don't give that to you, that should be your first priority. So let's take a look at an example, okay? I'll do one of each type, okay? So we can say the number of bacteria after 5 hours were the number of bacteria after 5 hours were, that's a really not very good sentence, let me write down, okay? If let's see if we can do that. If initially there were 1,000 bacteria and after 5 hours there were 1,600 bacteria, then find two things. One, the number of bacteria after 10 hours, and 2, find how long will it take for the bacteria population to reach 2,500. So we want to find two things. This is a very typical problem for population growth, okay? So let's write down what's given to us. They've said initially there were that many bacteria. So if you go back to that formula, I'll just write it on the side here. Q is equal to Q naught e to the KT. It's a growth problem, so it's KT, not negative KT. So Q naught is called the initial population. So we had initially 1,000 bacteria. Okay. Then they told us that after 5 hours, this is by the way Q of t, the population after time t. I think I did write that down for you guys, didn't I? Yep. Okay. So after 5 hours, so Q of 5, the population reached 1600. So Q is a population at whatever time you specify. In this case, after 5 hours, Q was 1600. Now we have two questions to answer. The first one is, find the number of bacteria after 10 hours. You want to find Q of 10. What was the population after 10 hours? And then the next question is, how long will it take for the bacteria population to reach that? So they want you to know at what time. We don't know that. Will the population reach 2500? Okay, so there's two questions to do. Now remember what I said earlier. Anytime you're doing population growth and decay problems, radioactive decay problems, you always have to find K first. And that's why they gave us this additional condition. So let's use that to find K first. Okay, so Q is 1600, Q naught is 1000, E, and then we don't know K, but we do know T here. T is 5. Okay, if you want, maybe this might be better to write down. They've given us Q is equal to 1600 and T is equal to 5. That's what this tells us. So let's plug it into a formula. So we have 1600 is equal to 1000 e to the 5k. So I need to find k. K is an unknown exponent, so we know we have to introduce logs, but to do that we have to isolate the exponential term. So let's divide both sides by 1000. So we get 1.6 is equal to e to the 5k. So now I can introduce logs. I get ln of 1.6 is equal to ln of e to the 5k. So I get ln of 1.6 is equal to 5k ln of e. We brought the exponent in the front. Ln of e is 1. So k is equal to ln of 1.6 over 5. Now please remember not to convert k to a decimal, because we're going to use k to answer these two questions that they've asked us. So if you convert that to a decimal, then you're going to have round off errors, because you can't carry unlimited number of decimals. Okay, so let's calculate the second part. So they've asked you to find Q when t is 10. They've asked you what is the population when t is 10. So let's do that. Same formula, Q is equal to Q naught e to the kt. It's a population growth problem, so same formula. We're looking for Q, so Q naught is 1000. We have e to the k. K is this, it's ln of 1.6 divided by 5 times 10. 5 goes into 10 two times. So we get 1000 times e to the 2 ln of 1.6. It's just a matter of punching this into your calculator, so let's do that. Okay, so if we take 1000 times ln, no, not ln, e raised to parentheses 2 times ln of 1.6, oops, close parentheses, so we get 2560. So we get 2560. So that's what the population will be after 10 hours. Okay, now I'm going to change this one to a little bit, since we already got close to 500. Let's say it's 5000 that they wanted us to find. Okay, so I'm just going to change that to 5000. So let's do that. So we answered the first question. The second question was, and also please note again, even before we answered these two questions, we had to find k though. Always remember that with population and radioactive problems, you always had to find k. So in the second problem, they've asked you, how long will it take for the population to reach 5000? So Q will be 5000. Q is the population. T is the time it takes for that, what we are looking for. Same formula, Q is equal to Q naught e to the kt. Q is 5000. Q naught is 1000. You have E. We do know K. K is right here, but for now I'll leave it as just K. I'll add it a little bit later. I want to solve for T. T is an unknown exponent, so we need to introduce logs. So we first need to isolate the exponential term. So divide both sides by 1000. So we get 5 is equal to kt. Let's introduce log. So we get ln of 5 is equal to ln of e to the kt. Bring the exponent in the front. So we get kt times ln of e. ln of e is 1. So divide both sides by k. Since we want to solve for t, we get this. So we've done this now 4 or 5 times, so you should get pretty comfortable with solving for some unknown exponent. Let's replace k with what we found earlier. K was ln of 1.6 divided by 5. Okay, so just so you guys know, when you have a divided by b divided by c, so that's a divided by b over c, that's what this is. You change the division to multiplication and you flip the second fraction, so you get ac over b. So basically the c flips and goes to the top, so this 5 will go to the top, so you get 5 ln of 5 divided by ln of 1.6. So let's punch this into a calculator and see how long it'll take for the population to reach 5,000. Okay, so we have 5 ln of 5 divided by ln of 1.6. So we get 17.12 hours. 17.12 hours. So that's how long it's going to take for the population to reach 5,000. So this is a very typical population model. They could have easily asked us, when will the population double? So in that case, we could have said instead of 5,000 it would be 2,000, since we started with the initial population of 1,000. So they could have asked us that, a lot of different questions. Okay, but the idea is the same. Remember to find k first. Okay, let me give you one problem on radioactive decay. So let's say that 20 grams of carbon 14 reduces to 15 grams after 100 days, 100 years, sorry. Okay, so that's what we have. Carbon 14 is used for trying to figure out how old a fossil is. Okay, so it's called carbon dating, to figure out how old something is. They measure the amount of carbon 14 left in that in the fossil, and then they can figure out how old that fossil was. Okay, so the question here is, if 20 grams of carbon 14 reduced to 15 grams after 100 years, find the age, find the time, find the time it takes for the amount of carbon 14 to reach 12 grams. And they've told us that half-life of C14, carbon 14, is 5,730 years. Okay, so they've told us that the half-life of carbon 14 is that. Okay, so now you have to realize we have to do what first? Find the K, and this is radioactive decay problem, so we need to use the appropriate formula. So the initial amount, the formula is this: Q of T, carbon, the amount of carbon at time T is equal to the amount you started with, e to the minus KT. So Q naught is the amount you started with. In this case, we started with 20 grams. Okay, and they've told us that Q after 100 years was 12 grams. The amount of carbon after 100 years was 10 grams. Okay, they want you to find how long the time it takes for the amount of carbon to be, 15 grams was after 100 years, to be 12 grams. How long will it take for the amount of carbon to be 12 grams? Okay, now they've told us, okay, they've told us that the half-life of carbon-14 is 5,730 years. Now that's important because earlier I gave you the formula for half-life. If the half-life is this, then what is K? K is ln of 2 over the half-life. So in this case, we don't even have to go through any work to find K. We already know K. K is ln of 2 over the half-life. So in this case, it will be ln of 2 over 5,730. So we know K. So let's just answer this question. So they've told you Q is 12, Q naught is 20, e to the negative kt. I do know K, but I'll plug it in later. So I want to solve for t, unknown exponents. I want to isolate this, divide both sides by 20. So 12 divided by 20 would be 6 over, 4 goes into 20 and 12, so it'll be 3 over 5 is equal to e to the minus kt. You introduce logs on both sides since we want to solve for t. So we get ln of 3/5 is equal to negative kt times ln of e. ln of e is 1 since the base and the number are the same, so t is equal to ln of 3/5 divided by negative k, since you want to solve for t. So what is t then? It's ln of 3/5 divided by minus ln of 2 over 5730, and this will flip and go to the top just like I showed you before. So you get 5730 times ln of 3/5 over minus ln of 2, and that'll tell you the time it'll take for it to reach 12 grams. So let's do that on a calculator. So let's clear. So we have 5730 times ln of 3 divided by 5. Okay, and you divide that by negative ln of 2. Okay, so we get 4,222 years, 4,222.81. 4,222.81 years. That's how long it'll take. Okay. Sometimes they could give you this problem. They could tell you that there is 90%. Oh, let's do this. 90% of the original C14 has decayed. Okay, find the age in a fossil has decayed in a fossil. Find the age of the fossil. Okay, so they found a fossil and they measured the amount of carbon in it, and they found that 90% of it had decayed. Okay, so remember now, the key thing is Q tells you how much carbon is left, not how much has decayed. So if 90% has decayed, how much is left currently? 10%. Okay, so let's write down what we know. So they found some fossil, and they found that at some time t, the amount of carbon is 10% of what you started with. So 10% of Q naught. Since 90% has decayed, only 10% of the original amount is left. So it'll be 10% of Q naught. Okay, we already know the half-life of carbon, which is what, 5,730 years. Once I know that, I know K. What is K? It's going to be T sub H ln of 2 divided by T sub H. So it'll be ln of 2 divided by 5,730. So let's do this problem. They want you to find how old the fossil is. Okay, So you're looking for T. So if you measure the amount of carbon today, you want to know how far back you have to go. So Q is equal to Q naught e to the negative KT. Q is 0.10 Q naught is equal to Q naught. We don't know Q naught, so we'll just leave them alone. E to the minus KT. I do know K, but I'll plug that in later. I want to solve for T, so I'm going to isolate the exponential term, so divide both sides by Q naught. So I did that, introduce logs on both sides. Okay, so we get ln of e to the minus kt, bring the exponent in the front. So you get minus kt times ln of e, which is 1. So now we divide both sides by k, negative k, so you get ln of 0.1 divided by negative k. But we know what k is, it's right here. So we get ln of 0.10 divided by minus ln of 2 over. So it's pretty much the same as the last problem. So you have 5730 times ln of 0.1 divided by minus ln of 2. So I can just pretty much use the last entry. I just changed this to 0.01, 0.1, and then everything else stays the same. So you get 19,034. So we get 19034 and some change. Was it 65 years? So that's how old that fossil was. Okay, so that's how we do these problems on radioactive decay. Just remember to find K first. Okay, the last type of problem in this section is on SC, on earthquake intensity. It's on earthquake intensity. Okay, so in that case the formula is given by this. We have M is equal to 2/3 log of E divided by E naught. Okay, so in this case the formula is given by this. M is equal to the log of E divided by E naught. Okay, so we want to identify each of these values. Okay, so on a Richter scale, Richter scale is a common measure that's used to measure is a device that's used to measure the intensity of an earthquake. Okay, so there are many different ways for computing this based on the different varieties of quantities. Okay, so in this case, E is the energy released, M and is measured in joules. So E is the energy released and is measured in joules, okay, during an earthquake. Then the magnitude of the earthquake is given by that. So M is the magnitude of the earthquake. Okay, and E naught is just a constant, which is 10 to the 44 joules. So that's just a constant. So these are the quantities here. So let's just quickly do one example on this. There's no unknown exponents here, so let's see what we need to do here. So the question is, if an 8 times 10 raised to 14 joules of energy is released, okay, during an earthquake, what was the magnitude? So that was a question. Okay, so let's do this. So they just want us to find the magnitude. M is equal to, the formula is right there, it's 2/3 log of E divided by E naught. Okay, so we have 2/3 L log of E in this is given to us by this, so it's 8 times 10 to the 14 divided by E naught, which is 10 to the 4.4. Okay, that's a constant that's oops, not 44, 4.4. Okay, so now that we have that, it's just a matter of plugging it into the calculator. There's not much to do here. So you can start by taking parentheses 2 divided by 3. So I'm just doing this on the outside separately. And then we're going to take the log of this numerator. So I'm going to need a parentheses 8 times 10 raised to 10 raised to 14, and then close the parentheses, divide that by 10 raised to 4.4. Oops, can't get that 1 to pop. 10 raised to 4.4. Oh, we have log of 10 raised to 14 times that. Did I have extra parentheses here? 1, 2. Oops, I have an extra one. So we get 7.002. Okay, so the magnitude is roughly 7.002. So it would be a magnitude 7 earthquake. That's how they calculate the magnitude of the earthquake. So let's take a look at one last example of this section. So they asked us how much energy is released in a 5.9 magnitude earthquake. If you want to find out how much energy that's released in a 5.9 magnitude earthquake, so let's take a look at that. Okay, so, and again, please make sure, I know I don't do that now, but you do need to write your answers in terms of a sentence. If they ask you a question in terms of a sentence, always get into habits of doing that. So in this case, they're looking for E. They've given us the magnitude of the earthquake, it's 5.9. And we already know the E constant, E naught, is 10 raised to 4.4. So let's plug this into a formula. We have M is equal to 2/3 log of E over E naught. So we're solving for E, which is inside the log. So this is a logarithmic equation. We have log and an equality. Let's replace things we know. We have 5.9 is equal to 2/3 log of E over 10.4, 10 raised to 4.4. So how do we solve this for E? I want to solve for E. E is inside the log, so my goal should be to get rid of the log term. And to do that, I need to write this without the log. And the best way to do that is first start by getting rid of this, isolate the log term. So I'm going to cross multiply the 3 and the 2. So I get 3 times 5.9 divided by 2 is equal to log of E divided by 10 raised to 4.4. Remember, we are trying to use the definition of logs to do that. These are the kind of problems we did in the last section when we had one log term. So that's what we're doing. So now the base over here is 10. So I can take this base and make it the base on this side. Okay, so I can do that. So I have 10 raised to 5.9 times 3 divided by 2, that's what we have, is equal to E over 4 raised to 4.4. So I took the base here, made the base on the other side, dropped the log term. Now it's just a matter of multiplying the left hand side by this quantity so we can solve for E. So E is equal to 10 raised to 4.4 multiplied by 10 raised to 5.9 times 3 over 2. So if I multiply these two, that'll tell me how much energy was released in that earthquake. So let's do that. So we have 10 raised to parentheses 4.4 times 10 raised to parentheses, it's 3 times 5.9, so you can go 3 times 5.9 divided by 2. So we get 5, 6, 2, 3, 4, 1. Okay. Make sure did I miss? Oh, I missed something, didn't I? Because I put a decimal there. That didn't look right. So it should be 3 divided by, 3 multiplied by 5.9. So I need to, oops, what did I do? Deleted that. So insert 5.9. So that's better. So it's roughly 1.78 times 10 raised to 13. So it's roughly 1.78 times 10 raised to 13 joules. So an earthquake of a magnitude 5.9 releases that much energy. Okay. So those are the kind of applications we can solve using logs. And in this last example, we had a logarithmic equation. Unlike in the previous examples, we were solving an exponential equation because the unknown was an exponent. So make sure you guys understand the differences.